Record.
All right. Good morning, Dr. Martin. This is Alexis Lovelace.
My name's Anwen.
And my name is Abdul Rahman Zakir.
And today we're going to be going over our project, which is the flash drum design that is built to recover hexane from the mixture of hexane, heptane, and hexanol. First, we need to identify what the flash drum is. A flash drum is a device that is used to separate a feed into a vapor phase and liquid phase. The most volatile component in the feed will be immediately vaporized once the feed is inside the drum. So if you zoom in to the part of the introduction, you see our design that has our temperature and pressure at the starting point of the feed. That temperature and pressure will go into the heater, which goes into the expansion valve, and the pressure will stay the same, which makes this process an isobaric process. The feed is expanding, which means it's depressurizing when passing through an expansion valve into the flash drum. Now, in the drum, it is separated into vapor phase and liquid phase at equilibrium and leaves the system at vapor stream at the top and liquid stream at the bottom. From the vapor phase, you will have a mixture of three components passing through a condenser to get the light key separated from the remaining components, and then at the bottom, you will have the liquid components that come out of the liquid phase.
To achieve our project, we have some goals to do. The main goal of the project is to recover as much out light key is hexane as possible into one streamline. Along with that, we had to find the dew point and the bubble point of the feed, and we need to find the operating conditions in the drum depending on the vapor and feed ratios. Finally, we will consider the impact of carbon monoxide gas inside the column when operated at temperature of 200 degrees Fahrenheit. Before that, we need to make some assumptions. The flash drum was operating adiabatically, which is the heat is equal zero. All our components, hexane, heptane, and hexanol were immiscible. We assume ideal gas behavior in vapor phase and ideal solution in the liquid phase. The flash drum was operating continuously and no heat losses to the surrounding. Mass is the same, which means the mass flow coming into the inlet will be coming out of the outlet. No mass was lost or gained, and the inlet energy could be equal to the outlet energies. We chosen the reference points at 25 degrees Celsius, which is 77 degrees Fahrenheit. We're doing the project by dividing them into 4 steps. We first analyzing thermodynamic properties of each pool component. We then using Aspen Plus to simulate the separation process, and we can obtain the temperatures and pressure of the drum. We apply in the thermodynamics calculation to verify and achieve our goals, and then generating the VLE diagram for our pseudo-binary mixture. The pseudo component would be including the hexane and heptane. We found that the drum operating at pressure point 0.9 bar, which is 13.05 psia, and the at temperature 127.5 degrees Celsius. So we have the feed coming in at about 0.4 hexanol in molar fractions in liquid phase, which is at this point. When we increase the temperatures in the heater, the feed will be inside the dome for the TXY diagram. And then we look at the PXY diagram. So at the 127.5 degrees Celsius and 1 bar, the feed will pass through a valve, expansion valve, which decrease pressure to 0.9, and the feed is in the dome but nearly dew point curve, which make which we can recover the most hexanol as possible.
Next, we will go into the thermodynamic calculations. So the first equation that we use is the Antoine's equation. Antoine's equation is the log of P sat over bar, which equals A minus B over T, which can be in Kelvin or Fahrenheit, plus C. The next equation that we use is F equals V plus L, which is the flow rate equals the vapor plus the liquid. Right under that is going to be the single component with the molar fractions. The molar fractions, Y, is going to be the vapor molar fraction, and for X is going to be the liquid molar fraction. Now, we need those molar fractions to find the bubble point and dew point. The equation for the bubble point is going to be X1 multiplied by P1 sat plus X2 times P2 sat plus X3 times P3 sat. You have three of these components because we do have three different type of mixtures. You have hexane, heptane, and hexanol. Then for the dew point, it's 1 over Y1 divided by P1 sat plus Y2 divided by P2 sat plus Y3 divided by P3 sat. And then the next equation that we use is going to be the equilibrium condition, which is Raoult's law, which is K equals Y over X. And then it's also PI sat over P. We used those equations to find the numbers that you see in the chart. For the bubble point, we got 2.11 bar. For the dew point, we got 0.78 bar. The liquid stream, which is L, is going to be 16.71. And then the vapor stream for V is 98.29.
All right. So next we have our energy balance and heat balance equations. Our first equation is enthalpy for the feed, in which HF is our enthalpy for the feed. The various Z values and the subscripts, by the way, 1, 2, and 3 correspond directly with hexane 1, heptane 2, and hexanol 3. So Z is our molar fractions, CP is our specific heat, or heat capacity, sorry. TF is our feed temp, and TREF is our reference temp. Moving on to our enthalpy for the liquid stream. X is again our molar fraction in the liquid phase. HL is the enthalpy for the liquid stream. CP is the heat capacity. TREF is the reference temp. TDrum is the temp of the drum, in which we're flashing. Next is the enthalpy for the vapor stream, in which HV is our enthalpy of the vapor stream. Y is our vapor in our Y is our vapor molar fractions, and then delta H's are our corresponding changes in the enthalpies for the various components for our vapor fractions. Then next we have our heat balance equation. So we have our delta H is our change in total heat. HL is the heat of the liquid out. HV is the heat of the vapor out, and then HF is heat from the feed in. Next equation, we have enthalpy of the heater, in which H1F is the enthalpy of the feed, QH is the heat from the heater, and HF is our enthalpy for the heater. Moving on to our next equation, enthalpy for the initial feed. Z, again, is our molar fractions. And then FCP is our heat capacities for uh, the liquid feed compositions. And TREF is our reference temp. And moving on to our final equation, for our entropy change, delta S is our change in entropy. CP is our heat capacity, or sorry, specific heat. T drum is our temp in the flash drum, and delta H is our total enthalpy, change in total enthalpy. And then if we move on over to our energy change results, our enthalpy change overall totaled out 3.49 megajoules. Our entropy change totaled out to about 8.92 kilojoules per mole. And our heat addition to the heater for the initial point of the process was 2.75 megajoules.
As I mentioned earlier, the flash drum were operating at 127.5 degrees Celsius at pressure 13.05 psia. We also designed our process with other two feed to ratio, the vapor to feed ratio. The first one, if we have the liquid stream and the vapor stream coming out equally, which means the ratio 8.5, we will operate in the column at 113.4 degrees Celsius and 13.05 psia. And if we want to liquefy 2/3 of the feed, we're gonna operating our drum at 106.13 degrees Celsius and 13.05 psia. Overall, we recover 27.12 pound mole per hour of hexane, which we got 90. So we recover 96.85% of those. For extra considerations, we consider carbon monoxide gas inside our column. So which the drum conditions, gas, carbon monoxide will stay as gas, so it will have a huge impact on separating the light keys. As we changing the temperature and pressures, the carbon monoxide gas just stay in the vapor phase, so we will need extra steps just to recover our hexanes in vapor stream.
All right, and now to go over our milestones and our deliverables. This project certainly allowed us to put in practice what we've learned so far in thermodynamics in terms of our knowledge about flash calculations, as well as applying PXY and TXY diagrams in an application process via VLE modeling and simulating some of these chemical processes that we utilized in Aspen Plus software. Moving on to the conclusions or conclusion and recommendation. We were tasked with initially designing a flash drum to separate a 3-component mixture. In our case, again, hexane, heptane, and hexanol, of which hexanol was our heavy key, hexane was our light key, and heptane was our tertiary component. The feed was initially available at a 70-degree Fahrenheit temperature and a pressure of about 15 pounds per square inch per area. The feed passed through a heater and then through an expansion valve where it finally arrived at the flash drum, which was being operated at about 200 degrees Fahrenheit. The mixture was quick to separate due to a pressure drop. Most of our light key was emitted and collected as a vapor, which was our goal, while majority of the hexanol and heptane fell into the liquid stream. Our overall collection of our lighter key, which was hexane, turned out to be about 27.12 pound moles per hour, after leaving the flash column, which is about 96.85% collection. That said, some things that came to the conclusion or was that for such a high yield, we had quite a large enthalpy change, again, about 3.49 megajoules. Our entropy change, 8.92 kilojoules, and the overall heat added was 2.75 megajoules. That was the strain placed upon the system to get the yield that we achieved for our light key, which was deemed quite high. So our recommendation was that if you run the overall process at a lower temperature, by lowering the heat addition and starting at a lower inlet temp, you can throw in a recycle stream so that even if the initial pass through the flash drum, if you don't collect as much light key as possible, you can rerun it, and that light key can be reflashed, reabsorbed from the heavier liquid stream.
And that should be done for our project. And thank you for listening.
Thank
Thank
you.
you, Dr. Martin.